All right, make sure you have whatever note sheets you are using. A pencil and a calculator is going to be needed for today. All right, an imaginary number is what we're starting off with. You are like, what the heck is an imaginary number? Well, it is a number. An imaginary number is one that would be, when it's squared, it gives a negative result, which in your head, that shouldn't make sense because any number times itself is always a positive, right? Positive 3 times positive 3 is positive 9. Negative 3 times negative 3 is positive 9. So how can I multiply a number to itself to get a negative result, right? Well, this is when your eyes are going to come in. It's called imaginary, okay? So when you square these imaginary numbers, you actually get a negative out of it. You're going to see them written as the letter I. So I is actually a number. It's not a variable, okay? If you have 2x and you have 2I written, those are two completely different things. Okay? 2x versus 2I, okay? Because x is a variable. X represents any number that it could possibly go there, right? I is a specific number all by itself. So that's why these things, they are not the same, okay? They are not the same. They are completely different. I is a number. Okay. So let's show how to use them real quick. So if I had the square root of negative 36 before today, you'd be like, I can't do that, right? But in reality, I can do it. The square root, I'm gonna break it apart. Square root of -1, square root of 36. The square root of 36 is 6, right? And right here, the square root of the -1, that's what turns into I. So this is what becomes I, this is 6. And we always write the coefficient first and then the I after it. So our answer here is 6I. All right, the one next to it, negative times a negative, oh my gosh, negative times the square root of -81, all right? There is a negative on the outside, so we're gonna leave that there. There's a negative on the inside, and there's an 81. Breaking apart like this, you don't have to do it. I just want you to see where our answers are coming from. Eventually, you'll just automatically know what to do, okay? But I'm splitting them all up. So the square of -1 just stays -1, right? The square root of -1 right here, that gives us our I, our imaginary number. And then the square root of 81 is 9. So when we put all these together, we're multiplying them, right? -1 times 9 is -9, and then I. So your answer becomes negative if there's a negative on the outside. All right, next we have 2 times the square root of -49. So we have 2 on the outside, there's a negative happening, and then there's 49. All right, well, 2 stays there. Square root of -1, there's our imaginary number. And the square root of 49 is 7. When we multiply these together, we get 14I, like that. All right. These next 3, they kind of remind you on how to simplify radicals at the same time. So I threw a little bit of review in here for you. So the square root of -20. So we have -1 and we have 20, right? There is no perfect square of 20, so you're gonna have to simplify it. So square root of -1 stays, but I can break apart 20 to be 4 and 5, right? And now I have a perfect square. The square root of -1 is I. The square root of 4 is just 2. And then the square root of 5 just stays the square root of 5. So our answer becomes 2I square root 5, like that. Okay, how we doing? I'm looking at all your faces, or all the faces that I can see.
I didn't know if you said this, but what does it mean if the I is negative? Does that mean anything or no?
What do you mean if the I is negative?
Like third problem on the top, I was negative, or was that subtraction?
No,
Oh,
so
that looked like
I
a.
is
Never
I
mind.
is equal. Oh, I see what you see. I see what you
That look.
see. That right there. Gotcha. Yep, no, that should just be a multiplying. You're right. All right, someone said what happened to the 4. Oh, okay. So in the problem that we just did, I simplified my radical. So I split apart 20 to be 4 times 5. And then the square root of 4 turned into just a 2 because the square root of 4 is 2. So I'm just simplifying. I'm still simplifying. Good questions. Any other questions?
Why is the 2 on the other side of the I?
That's just how we write it. We always write the constant first, then the I, and then the radical. That's just the order it's written. Yep. So just because, just to make your life a little bit more difficult. These are good. Any more? See if anyone has their hand raised. I don't see. Y'all know you have that feature, right, on Zoom? You can like click something and it raises your hand. All right. All right. Can we see the last two still? I didn't mess anything up, right? You can still see my page. All right, negative times the negative, oh my gosh, negative times the square root of negative 28. All right, so again, I'm going to break it up. So I have a negative on the outside. That's the same thing as multiplying by -1. We have a negative on the inside, so we're going to keep that by itself. And then we're going to have the square root of 28. That is not a pretty 8. There we go. All right, so we're going to break down each piece more if we can. The -1 on the outside is a coefficient. I can't change it anymore, so it's just going to stay -1. It just stays there. The square root of -1, that's new today, that is I. That is the number I. It represents the square root of a -1. And then the square root of 28 does not give me a pretty number. You're not going to give me decimals because I don't want them and I'll mark it wrong. We have to simplify the radical. So we're going to break it apart. So we're going to think, okay, what times what is going to be 28? There's lots of different answers. I am personally going to choose 4 and 7. Because if I can get a perfect square to show up again, that's what I want to do. Could I have used 2 and 14? Sure. I would have to just keep breaking down my numbers, okay? But if you can break it apart to get a perfect square, do it. So there's my square root of 4 again, like I got last problem, this one. So that is going to simplify. So we're going to go through -1s on the outside. We still have I. The square root of 4 is the number 2. Square root of 7, I can't break that down anymore, so it's just going to stay square root of 7. So we multiply it on the outside. I have -1, I, and 2. So that is going to simplify to be -2i, and then square root of 7. And then side. All right. One more of these. All right, so we already have a coefficient on the outside. It's a +2. It's going to stay there. I see a negative 75 inside, so we're going to break that apart. I'm going to take the negative away, give it its own radical of -1, and then I'm going to have 75 by itself. All right, 2 stays 2. Square root of -1 is I. Here comes our imaginary. There is no square root of 75. That's a whole number. So we're going to break it apart. Lots of ways to do it. I think I know it's divisible by 5, but I'm going to use 25 and 3, right? If I do 25 and 3, I have found a perfect square again. The square root of 25 is a perfect square. The square root of 25 simplifies to just 5. So combine what's on the outside, 2 times I times 5 will be 10I, and then we have square root of 3. Let's say. All right. All right, questions. Take a moment to pause. Look in the chat box, looking at your faces. Any questions? No? Okay. Okay, then we're going to continue. Okay. Okay, so now that we have worked with the number I, and we know what it is, we know it is the square root of -1, okay? If we pair that imaginary number with a real number, we get something called a complex number, okay? And they can be plotted on a plane. I'm going to show you in a minute. They're written like this, 12 plus 9i, okay? So that is a complex number where 12 is your real number and 9i is our imaginary number because it has the I, right? So we can put them together. I'm going to try to show you a video. I need y'all let me know if you can hear it, because last time we did this, I know you could not hear the sound. So we're going to try this again. All right. Could we hear the video when it was playing just now? The ads? No, I'm seeing no. Why? Why doesn't it want to show you? All right. Hold on. Check your audio settings in Zoom. Okay. Let me do that. All right.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis, so according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are two perfectly good values of x that we could plug into our function and get 0 out. Where could these two missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full two-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention. So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral, so from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers.
Okay. So there is a part 2 to this. I'm not going to show it to you on Zoom, but I can put it on my my playlist if you want to watch part 2 and learn some more about it. But it just kind of gives you a little bit idea of what the imaginaries are, how they came about, and all that jazz. Okay, I like you guys to understand the why sometimes, like, you know, what are these things besides me just saying, oh, it's the square root of -1. I like you to know exactly like what it came from, why it's being used. So sometimes I'll throw in a little history lesson for you guys. Okay, so we are going to play around with I a little bit more. So there is a cycle of I. There is a pattern that forms. When we break it down and we simplify it, we're going to get a pattern where it goes I, -1, -I, 1. And there's a little saying like, I won, I won. You just got to remember which ones are negative. But you're going to see this cycle kind of form over and over and over again. And I'm going to show you how. So if I give you this just I, well, we know I is equal to the square root of -1, right? So it's going to be simplified as just I. That's like saying I to the first power, right? Anything to the first power is just itself. I squared, okay? That is saying square root of -1 times the square root of -1, okay? Well, any radical times itself, the radicand gets to be canceled, right? That's the same thing as saying the square root. That's saying the square root of -1 squared. So the square root and the square cancel out, and it simplifies to just the number -1. All right. I cubed, I'm going to use my previous answers to actually help me with this one, because I could split apart I cubed to be I to the power of 1 times I squared. Because remember, when we multiply, we get to add our exponents together, so I can use that same property to split them up. So I to the power of 3, I can rewrite it as I to the power of 1 times I to the power of 2, get my 3. And my previous spots on my table shows me that I to the power of 1, well, that's just I, right? And I squared, we see simplifies to be -1. So this simplifies to be I times -1, which is -I. -1I or just -I. All right, I to the 4th. Again, I'm going to break it apart using my exponents. So we could do I to the 1st times I cubed, or we could do I squared times I squared. Either one of these is going to work out for us. I'm going to use I squared twice. I'm going to break apart 4 to be 2 and 2. And I know from up here, my second one, I squared was equal to -1. So that's the same thing as saying -1 times -1, which is equal to 1. We'll see how the cycle is forming, and it's going to keep going. So watch what happens with I to the 5th. I to the 5th, I'm going to break apart. Let's do 4 and 1. Is that okay? You could also use 3 and 2. I'm going to say I to the 4th times I to the 1st, because 4 plus 1 is 5. I to the 4th, we just figured out was the number 1, and I to the 1st is I. 1 times I. There we go. There's my I again. My cycle is starting over. I to the 6th. Again, we can break this apart. 5 and 1, 4 and 2, 3 and 3. So many ways. I'm going to do 5 and 1. I to the 5th in my chart, I just figured out was I. I to the power of 1 is just I. So this is going to be equal to I squared. Okay, well, that's not simplified. Because I squared, I can simplify again, and that's going to be equal to -1. I to the 7th, we're going to rewrite this. Let's use, I'm going to use 3 and 4 this time. So I cubed times I to the power of 4. Well, I know I cubed simplifies to -I. And we know I to the fourth simplifies to just 1. So negative I times 1 gives me negative 1I or negative I. All right, and then we have I to the 8th. Break that apart. I'm gonna use 4 and 4 for this one. So I to the 4th times I to the 4th. We know that is going to be 1 times 1, which simplifies to just 1. So this cycle of 4, it keeps repeating itself over and over and over and over again. Okay, why do I need to know that? Well, because if I ask you to simplify something that's large, that number 4 is going to come in handy. Some of y'all are still writing, so I'm going to give you a second to write. Okay. Remember, if I ever move on and you're not ready for me to, I will upload this later. And when the Zoom call is over, you can always stay and ask me to go back to something. All right, we only got 2 more slides. Here we go. So how are we going to use this to reduce large numbers? So I to the 20th, I would love to not split that up to like I to the 2nd power 10 times. That's annoying, right? Or I to the 4 5 times. That's kind of annoying. So instead, what you're going to do is you're going to take your exponent and you're actually going to divide it by 4. Okay. So what we're going to do is we're going to take 20. I want you to divide it by 4. Okay. When you divide 20 by 4, we get the number 5. It's actually 5.0, right? That 0.0 is what's going to help you simplify your I. Because that's going to be your remainder over 4. So 0 over 4 is what this, right? I can write 0.0, I could say 0 over 4 is the same thing. Do we agree? So my new exponent for this is actually I to the power of 0. And anything to the power of 0 is just going to be equal to 1 every time. Okay. Let's see what happens when I divide by 34, excuse me. So I'm going to change my color. If I take 34, I'm going to divide that by 4. What do we get? 8.5, I think. It's too early to think. I'm pretty sure it's 8.5. But I'm going to make sure I'm right. I am right. It is 8.5. 8.5. All right, so how could I put 0.5 in some kind of a fraction with the 4? Well, what's half of 4? It's 2. So 0.5, so remember, we're looking at our decimals here. 0.5 can be written as 2 over 4. I'm using the number 4 because of that cycle. So that's going to be equal to I to the power of 2. And I squared is negative 1. All right, 41. We're going to take that and divide it by 4. Remember, we're doing this because we don't want to try to rewrite when it comes to large numbers like we were doing in the chart before. The chart before showed us the cycle. Now we're going to use that cycle to simplify things a little bit quicker. So we know it's a cycle of 4. So we're going to divide my exponent by 4. This time we get 10.25. All right, again, we're focused on our decimal here. 0.25 as a fraction with 4 is the same thing as saying 1/4. So my exponent, so this can be simplified. I can take I to the 41 and say it's the same thing as saying I to the power of 1, which is just I. All right, 59. Let's do some purple. So 59 divided by 4. So give me 14.75. So if we look at 0.75, how can we rewrite that as a fraction with 4? Well, 0.7 over 5 is going to be 3 over 4, right? Do we agree that's the same thing? So that means that the I to the power of 59 is the same thing as I to the power of 3. And then my chart from before, we know that's going to be negative I. All right. All right, if we do 63 divided by 4. 63 divided by 4 gives me 15.75. There's my 7.5 again, so I know that's going to be the power of 3, which is negative I. Woo. That is not a pretty I. There we go. All right, so are we seeing the pattern? Seeing how we can use our cycle of 4 to simplify our large exponents? Got 3 more, 78. So take 78, divide it by 4. That gives us 19.5. 0.5, like over here, that's the same as having 2 over 4, so it's the same exponent as 2, because 0.5 is 2 over 4, and I squared is negative 1. The only thing you have to memorize, if you're going to memorize anything, is going to be the initial cycle up here. So if you want to memorize something, it is that. And we just found out that I to the 4th is the same thing as I to the 0, which makes sense. If I went backwards in my cycle, if I went up 1, whoop, that would be where I to the 0 is. So that's the only thing you'll have to really understand and memorize. But if you don't remember, as long as you know I is equal to the square root of negative 1, you can create your first 4 using what we did in this table with what you already know to help you remember what the pattern is. All right, 2 more, here we go. 85, take 85 and divide it by 4. And that's gonna give me 21.25. Remember, all we care about is the decimal, which is 0.25, and that's gonna be the same thing as 1/4. So that means it can be simplified to I with an exponent of 1, which is going to be equal to just I. And our last one, 1,526. Okay. Seems a little crazy. 1,526 divided by 4 gives me 381.5. Now again, the only part we care about is the decimal. I don't care that it's 300 and whatever. I care that it's 0.5. Because 0.5 tells me that's the same thing as 2/4. So it's going to be simplified to the same thing as I squared, which is negative 1. All right. I'm going to pause and see if there's any questions from anybody. So I have the chat open. I have your faces open. If anyone needs to raise their hand. The pattern will never change. It's always going to go, it's always going to be those same 4 numbers, and it's always going to go in that same order. So I for the power of 1, negative, I, negative 1, negative I, positive 1. And that starts over again. I, -1, -I, +1. We use 4 to divide because the cycle consists of 4 numbers before it starts over again. So we know it's going to be one of those original 4. Someone asked why are we dividing by 4? That's why, because the I cycle is 4 different pieces. These are good questions. Any more? Okay, so someone asked how are we simplifying 0.5 to 2/4? 0.5 is half, right? It's half of something. And I know 1/2 is the simplified version, but since we want things to be with our cycle of 4, our denominator stays 4. So half of 4 is 2. The 2/4 is the same thing as 0.5 when it comes to a decimal. Anything else? Okay. All right, so these notes are actually done. This is part of your homework, okay? So there are 15 on here. You're going to simplify I. So all of these, when the I is by itself, you are going to divide by 4, right? There are some towards the bottom, which I don't know why I don't have it here. There we go. Give me a second. There are some towards the bottom that I think might take you for a loop. I'm just going to remind you of something. Okay. These are, can y'all see it? I know it's small. These are the last 3 on your assignment. Your assignment, you need to submit your assignment. So it's the last 15 problems is what you're going to turn into me. The last 3 look like this. I don't want you to freak out. I want you to simplify each piece for number 13 and then add it together. Okay? Simplify each piece in 14 and then multiply. So I to the 8th, that's the same thing as, I believe, the number 1. I to the 9th is going to simplify to just I. And I to the 10th, right, hold on, 0.25, yeah. And then I to the 10th is going to simplify to I squared, which is -1. So I want you to simplify each piece and then add them together. Same thing with 14, which is actually, it's the same numbers. You're going to take 1, I, and -1, but here you're going to multiply them together. Okay. Number 15, when we're multiplying, y'all, we got to remember our properties of exponents. So I'm going to help you. So 2i squared, leave that alone, but look right here. You have 3i in parentheses and then an exponent on the outside. So that's the same thing as both of those having the exponent of 3. And that's all I'm going to help you with that one. You're going to have to keep going. But my suggestion is to simplify all of your i's first and then multiply or add or whatever afterwards. Okay? So this last piece ended up being the last part of your notes. These last 15 problems, these are your first assignment. Remember, you have a second lesson and a second assignment today still. Okay, this is just the first one. So finish this, turn this in, okay? And you can find all due dates. All that information is on Canvas. So I need y'all, you go to Canvas, it tells you when everything is due. All right, when you click on the assignment, it tells it to you. All right, so here, ooh, go away. So right here, oh, it's the calendar. The calendar can tell you also. So right here, it tells you that both of your assignments today are due on September 8th. So if you ever need to know when anything is due, click on your calendar and it's going to tell you. I'm pretty sure all of our stuff is going to be in green. All right. Again, please don't forget your second assignment. There is a part 2 to today's stuff. It is down here, part 2 video, and there's a part 2 assignment. Let me know. It's 8:23, so y'all have the rest of the period to work on the second assignment. If you have questions, send me a message. I do have a class at 9:20. You do too, so I can't answer it past then. If you need to Zoom one-on-one before then, send me a message and we can Zoom one-on-one and I can answer any questions y'all might have. Okay? Make sure you are signed up for Remind, because if you try to send me a message through Canvas and it's after 2 o'clock, I'm probably not going to see it. All right? So if you all need to reach me after school hours, it needs to be through Remind, because that goes straight to my phone and I can answer it easily. All right. So any other questions before I let you go? Okay. Well, if you don't have any questions, then I am done for the day. Get your 2 assignments done. Where are we signed up for Remind? Okay, so if you go to my page again, you go to the home page and you click on the Remind button right here, it gives you your code. So you're going to use the code at ALG2Douglas, and you can use the app or you can send it to the number 81010. All right. Okay, so if you don't need me anymore, you are free to go.